Oh, this is question 16, or sorry, assignment 16, question 43 from the Silberberg, and 5.43. In this case here, you have a hot piece of copper that was put into a vessel filled with water, and the water and vessel are at a lower temperature, and you want to know what the final temperature of the entire system is. So we know that all the heat from the copper, it's going to start losing its heat, and it's going to go towards heating up the water and the vessels. At the end, everything has the same temperature. If I was writing that out then, we know that the copper is going to lose its heat, and the water and the vessel, we'll call that the calorimeter, because that's really what it is in this case. It's the container where this is occurring. Calorimeter, those guys are going to absorb the heat. So you can write out, also you want to know that you're not creating or losing any heat in particular, it's always just being transferred. So all of that, all the heats should be equal to 0 when added together. But what are these equations for the heat of the different parts of the system? Well, copper, so if you want to find the heat for copper, MC delta T. The reason I know that, look at your units that you're given for C. You're given in units of per gram. Okay, so this is a per gram heat capacity. That means you're going to multiply it by grams. Okay, if it was a per mole, then you're going to want to multiply it by moles. You're going to want to switch your mass into moles. So just pay close attention to what units you're given for your heat capacity. So that's how you're going to find the one for copper, which is mass of copper. The delta T of the copper, you don't know T2, but you know T1. So you're going to have a T2 function within here, right? For your water, same thing. MC delta T. You're given units of per gram, so you're going to multiply by the grams. And in there, you're going to have a T2. All the T2s are going to be the same. All the T1s are slightly different, right? Well, at least between the copper and the vessel and water. These guys have the same T1. And your vessel, or your calorimeter, in this case here, this is big C. So this is big heat capacity. So specific, or for this actual vessel, the size it is, the material it's made out of. So it never changes for that vessel. So it's just joules per Kelvin. There's no how many grams of it or how many moles of it. It's just what it is. So this is going to be big C times delta T. From there also you have that T2. So it's all of that's in the equation. The only variable you do have is T2. Solve for T2, and that should be 36.6 degrees Celsius in the end.